Alright, so this problem says the current through a 5 millihenry inductors varies with time as shown below. So here's how I is changing with time. The resistance of the inductor is 5 ohms. Calculate the voltage across the inductor at t equal to 2 milliseconds, 4 milliseconds, and 8 milliseconds. So t equal to 2 milliseconds, 4 milliseconds, and 8 milliseconds. Okay, so essentially what we'll need is, at these times, you'll need di by dt. Di by dt is the slope of those lines. So let's find the slope of these lines at these times, okay? So t equal to 2 milliseconds, di by dt is equal to slope, and the slope of that line is, you can see that line is roughly, okay, we'll say 4 divided by 2, right? Or 6 divided by 3, same thing, okay? 6 amp divided by 3 milliseconds, 2 times 10 to the 3 amps per second, okay? So, and similarly, slope at what is that? 6, 3, minus 3, 6, and 3. So minus 3, and what is the time? 3 to 6 minus, okay, minus 1,000. Oops. Minus 3 amps divided by 3 milliseconds equal to minus 1,000 amps per second. And at t equal to 8 milliseconds, di by dt is the slope of that line, and the slope of this line is that is negative 3 over 6. Okay, so negative 3 amps over 6, so 500. Okay. All right, we have di by dt. Now we're going to use this to calculate various stuff. You guys understood that? Any questions? This, okay, so if you're trying to find the slope of this guy, delta y is that, which is 3 amps, and the time, change in time is this, 6 milliseconds, 6 to 12. So slope is delta y over delta x. Y is I in this case, okay? You guys understand? All right. Okay, what is it that we want to do? What is it that we want to find? We just set up the problem. The current through the 5 millihenry inductor varies with time as shown below. The resistance of the inductor is 5 ohms. Calculate the voltage across the inductor at these times. Okay, so let's so here, yeah, so that's, we got to be careful of this. Okay, so let's make sure we understand this. All right, now I'm not going to draw a solenoid just because, so okay, here's the inductor, but it's not an ideal inductor. It has a resistance as well. Okay, 5 ohms. So now this is not two pieces of equipment. This is one piece of equipment. Okay, its resistance is 5 ohms, and its inductance is 5 millihenry. Okay. Now, if when di by dt is positive, when the current is increasing, then for di by dt positive, the induced EMF will be in this direction, in the opposite direction. When di by dt is negative, induced EMF will be in that direction. Okay, did you guys understand that? Yeah, so if it's increasing, then if the current is increasing, then the battery EMF will be in that direction, in this direction. Okay. All right. So, all right. Now, what we are trying to find is the voltage across this this piece of equipment, and let me the EMF across the inductor. So the voltage AB is, the current is flowing in this direction. So across the resistor, the current is falling. So it's minus IR. And minus L times di by dt. That's the voltage across the inductor. Minus L di by dt. Okay. So now we just have to add the two terms. Okay. So let's be careful and make sure at each we understand what's happening at each time. Okay. So this is the expression, and we'll apply in each case. So voltage across AB. All right. For t equal to, what was the first time? 2 milliseconds. For t equal to 2 milliseconds, di by dt is positive. Okay, the current is increasing. The voltage will be, so I'll draw this now. So in the inductor, the induced voltage will be in the opposite direction. Okay. All right. So VAB equal to minus IR. At 2 milliseconds, what is the current? At 2 milliseconds, the current is 4 amps. Okay. So it's minus 4 amps times R, which is 5 ohms, and minus L is 5 millihenries. So this is the effect of the resistor, this is the effect of the inductor. And di by dt is 2000 amps per second. 2 times 10 to the 3 amps per second. Okay. This is the resistor, this is the inductor. Okay, so that's the symbol for the resistor. And that's the voltage across the resistor, this is the voltage across the inductor. And this, of course, would be 0. This voltage would be 0 when? when the current through this thing is steady. Okay, when the current through the inductor is not changing, this term is 0. Di by dt is 0, di by dt is 0, and that term will be 0. Okay. All right, so I'm going to write this separately just so we get, this is 20 volts and this is 10 volts. So because the current was changing at this time, the voltage at this instant, the voltage across this is 20 volts and this, the voltage across this element is 10 volts. It's all one piece of equipment. The voltage, because the wire is wound up, the voltage is 10 volts. Okay? Because of the self-inductance of the coil. If the coil was just purely resistive, then this wouldn't be there. Okay. All right, we'll calculate the voltage for the other two times. So what are the other two times? 4 milliseconds and 8 milliseconds. At t equal to 4 milliseconds, okay, again, VAB equal to my same expression. So this guy is the same. Well, no. At 4 milliseconds, what is the current? At 4 milliseconds, the current is 5 amps. Okay? Minus L di by dt, 5 millihenries. And di by dt is negative 1000 amps per second. Okay. So at this time, what we are saying is the voltage is in that direction across the inductor. So negative 1000 amps per second. So as you go across this element, you're adding the voltage, and minus or minus becomes plus. Okay. So this is minus 25 volts, and this is plus 5 volts. Okay, so what we're saying is if the current decreased fast enough, this voltage would cancel this voltage, and you can have 0 volts across that. Yep. All right, let's do the last case at, well, I'll do it on a new sheet because I'm going to run out of space here. All right, so t equal to 8 milliseconds. At t equal to 8 milliseconds, the current is 2 amps. And di by dt was negative 500. Okay, so 2 amps, 5 ohms, minus 5 millihenries, and di by dt was 500, half a milliamp per second. Oops. half a kiloamp. That's 500 amp. Okay. So now this is equal to minus 10 volts, and this is equal to plus 2.5 volts. So with an inductor present, if a current is changing, you're inducing EMFs and so on, and you have to take into that into account. Okay. So the message is, you take a wire, if you have a straight wire, it doesn't misbehave, but you wind it into a coil, and suddenly now it is acquiring all these properties that you have to be aware of. Yeah. Any questions before we move on? I was going to give you a break, but we are recording. I don't know how to stop recording it and so on, so we will keep going. Okay? Yep. All right.
Science is so crazy.
What's that?
How is science so crazy?
It is crazy, but it's a beautiful crazy. Oh man, quite a few problems, eh? What's that? Yeah, that's a lot of problems. Why did you pick so many problems, Olga? Yeah, but then, all right. You want to go use the restroom, okay.